So the next speaker today is KyeongRo Kim from Seoul National University, and he will be speaking about an invitation to Laminar group theory.
Thank you for introducing me. Today, I'm going to talk about laminar group theory. So this is joint work with Harry Young-Beck and Hong-Taek Jeong. Okay, let's start with the main question. Main question in the laminar group theory. In laminar group theory, we're concerned the following typical following question. The question is characterization problem. So when is a subgroup in orientation preserving circle homeomorphism group is a hyperbolic surface, a fundamental group of hyperbolic surface or hyperbolic three manifold. So in laminar groups theory, typically concerned about the characterization of the hyperbolic surface group and hyperbolic three manifold group in orientation preserving circle homeomorphism group. So by the way, what's the typical or standard circle action of the surface group or three manifolds group in the circle? So let me explain about the surface group case. Okay, now we concern the pi1 of hyperbolic surface in homeo plus S1. So first, we take a genus G surface, genus G hyperbolic surface, then the universal cover when the genus is bigger than 2, bigger than 1, then by uniformization theorem, we can identify the universal cover with the hyperbolic plane, and also the fundamental group of surface pi1 SG is act by isometry, hyperbolic isometry. So this implies the pi1s as a subgroup of PSR2R, subgroup of isometric group of hyperbolic plane, which is equal to PSR2R. So now note this, given G in PSR2R, we can think about the continuous extension on the into the Gromov boundary of the hyperbolic plane. So we can have some continuous extension of this elementary on the compactified hyperbolic plane, which is the so, and then we restrict this element into the boundary. Then we can get some orientation preserving circle homeomorphism corresponding to the an element of PSR2R. So in this sense, we can think of we can think of PSL2R as a subgroup of homeo plus S1. And so using this relation, we can think the pi1SG as a subgroup of homeo plus S1. So this is the typical kind of geometric action, typical action, which is induced by induced in some geometric situation. So then next, I want to talk about the hyperbolic string manifold case. So what is the typical action of hyperbolic string manifold action in the circle? So I want hyperbolic string manifold case. So actually by virtual fibering theorem, which is proven by KyeongRo. So every hyperbolic string manifold has a finite cover, which is mapping torus of some surface and with some pseudo-anosub monodromy. So I'd like to talk about the mapping torus case, hyperbolic mapping torus case. So here is our surface, and then pick a pseudo-anosub element from mapping class of the surface, a mapping class group of the surface. Then this pseudo-anosub element preserve two geodesic measured laminations, which is on the surface. And then the mapping torus is a hyperbolic string manifold. The fundamental group of this mapping torus is a cyclic extension, kind of cyclic extension of the surface fundamental group. The representation looks like group presentation is okay. Here is our surface. Now we choose standard generating set like this, and then now we ravel each loop by like this AI BI. Then there are G pairs of AI and BI. Then AI and BI. Here is AI. A1, B1, AG, BG. This is the genus of the surface. And then now we add the what T, alphabet T. T is the generator along the fiber, along the mapping torus. Mapping torus is made by some product space, which is here is I is the interval, and then we identify the upper surface and lower surface and bottom part, like by using this pseudo-anosub homeomorphism, like this. So this is a mapping torus. So the here T is the loop along this I. So this T means means the loop go around 1 times along the mapping torus. So the relation is this: T AI and T PI T inverse T PI. This is the relation. This is the group presentation of the mapping torus, the fundamental group of mapping torus. Then now, where's the action, circle action of this mapping torus? So again, here's the surface, our surface. Then the universal cover is the hyperbolic plane, and then the depth transformation act on the hyperbolic plane. Also, the pseudo-analysis element, we can lift the homeomorphism onto the universal cover. So we have some rift of the pseudo-analysis element on the hyperbolic plane, and then we think about the extension of the pseudo-analysis onto the ground boundary, and now restrict this element, this extension into the boundary. Then we can get also orientation preserving circle homeomorphism. Now we consider the, so we have pi 1 SG as a subgroup of homeo plus S1. And also B tilde. Then the group generated by these two components then also is also a subgroup of homeo plus S1, and this is obviously the pi 1 of mapping torus. So this is the typical action or geometric action of the hyperbolic mapping torus group, hyperbolic mapping torus group. So okay, now again we go back to the main question. So in that for surface case, the there are characterization about the action by convergence group theory. Okay, this is the in that answer for the surface case. We have the famous solution, which is, here is the theorem, which is called convergence group theorem, and this theorem is proven by Gabay, Thurston, and Junglis, and Tukia, and so on. So the theorem says that a convergence group is in the circle as a function group. So, but how about the hyperbolic string manifold case? There are no this kind of theorem, and also there's no this kind of theorem because the action of the rifting, action of the pseudo self pseudo self is not like a convergence group action. So to characterize the circular action of hyperbolic string manifold, we need the other idea. So our idea is using circle laminations. So now our problem is we wanna characterize the low-dimensional hyperbolic manifold group in terms of circle laminations, invariant circle laminations. Okay, why? Okay, let's get back the example of the mapping torus. Here is we have transverse geodesic lamination on the surface, which is preserved by the pseudo-honest element, and then the lift of the pre-image of this geodesic lamination induced to geodesic lamination on the hyperbolic plane. This geodesic lamination preserved by deck transformation, obviously, also is preserved by the rifting of pseudo-honest element. So this pi1 and v, the fundamental group of the hyperbolic mapping torus, also preserve this parallel geodesic lamination on the hyperbolic plane. And then, moreover, now here is the remark. Okay, if we have geodesic on the hyperbolic plane, then this gives parallel points, which is end point of this geodesic. Then conversely, we have 2 points of parallel points in the boundary. We can determine geodesic joining them. So we can think about the set of geodesic. We can think of the set of geodesic as a set of parallel points. Okay, here is a set of 2 points set of S1. So in this sense, we can think of geodesic laminations on the plane, a hyperbolic plane, as a subset of this M. So this is a completely the some kind of object in the circle. This is the intrinsic object in the circle. So pi1, the circle action of pi1 MV is not a convergence group action, but it preserves these 2 lamination. So this kind of lamination, this kind of subset of M is called circle lamination. So now I'd like to introduce a laminar group. A laminar group is a subgroup of homeo plus S1, preserving a circle lamination. So using this, finally, I'd like to introduce a recent result about this laminar group for the action of the rho, for the action of the low dimensional hyperbolic manifold groups. So first, back at me. Show the laminar group G with preserving three circle lamination simultaneously with satisfying some condition is a convergence group. So by convergence group theory, by convergence group theorem, we can conclude this group is a function group, which is the fundamental group of which is a kind of fundamental group of hyperbolic surface group. And then also conversely, any function group in the paper, this kind of group is called a pent-like COL3 group. So a function group, conversely, a function group G, such that the quotient, the associated space is not very simple. Is also a pent-like COL3 group. So this gives some new characterization for the surface circular action of the surface group, hyperbolic surface group. And for the hyperbolic string manifold case, very recently, Beck and Zhang and me showed the following thing. A laminar group torsion free laminar group preserving two lamination satisfying some condition. is the fundamental group of a bearing triangulated string manifold with a proper dam filling. This is kind of a solution for our main question. So for the string manifold case, so okay, this is a recent result, but there are however the statement must need this kind of technical condition still. So we have to I hope to remove this technical condition. So this is what I prepared. So thank you for listening. Any question?
Was there any questions? I did have one question.
Okay.
It may be a silly question as I'm not familiar with these things, but these laminar groups you talk about, are these discrete groups or do you have some non-discrete topology on them you usually consider?
In some case, we can when we have some special condition, we can prove this group is a discrete group of circle homeomorphisms S1, but in that usually laminar group contains pseudo-ensemble like element, but this kind of element break the discreteness. So you typically for string manifold case, these are not discrete. So, but however, for the surface case, there are discrete, usually discrete group.
Yep. Okay, thank you.
Okay, good.
Was there any other questions? Well, if there's no questions, let's thank KyeongRo again